What if nothing ever had to exist? No space, no time, no matter. And yet, here we are.
Physics can explain how galaxies form,
But not why anything exists at all.
This isn't just a philosophical thought experiment, it's not just a late-night dorm room conversation. It is, quite possibly, the most fundamental question humans have ever conceived. It sits at the absolute boundary of our knowledge, a place where physics, cosmology, and philosophy all converge, and sometimes collide. For millennia, we've looked to myths, religions, and ancient wisdom for answers. But today, we have a new set of tools. Using modern cosmology, cutting-edge discoveries from particle accelerators, and mind-bending ideas from the frontiers of theoretical physics, we're going to explore what we know and confront the profound mystery of what we don't. Science may not be able to fully answer the universe exists, but it has given us an incredibly powerful and detailed answer to it began and evolved. According to our best evidence, our universe as we know it started 13.8 billion years ago with the Big Bang. Now, the name is a bit of a misnomer. This wasn't an explosion space, like a bomb going off in an empty room. It was an expansion space itself. Imagine the surface of a balloon being inflated. Every point on the surface moves away from every other point. But there's no central point of the explosion. The universe began in a state of unimaginable density and heat, and it has been expanding and cooling ever since. This isn't just a guess, it's a theory supported by multiple, independent lines of evidence. First, we observe that distant galaxies are all moving away from us, and the farther away they are, the faster they recede. This is called redshift. The light from these galaxies is stretched to longer, redder wavelengths as the space between us and them expands. This is exactly what you'd expect to see in a universe that began with a Big Bang. Second, we've detected the cosmic microwave background, or CMB. This is the faint residual heat, an afterglow, from the very early universe, when it was a hot, dense soup of particles and radiation. Today, it fills all of space with a uniform temperature of just 2.7 Kelvin, a whisper of the universe's fiery birth. And third, the abundance of the lightest elements. The Big Bang model makes precise predictions about the amount of hydrogen, helium, and lithium that should have been created in the first few minutes. Our observations of the oldest stars and gas clouds match these predictions perfectly. In the 2020s, the James Webb Space Telescope pushed this story even further back in time. It's like a cosmic time machine, capturing light that has traveled for over 13 billion years. It has observed some of the earliest galaxies ever formed, just a few 100 million years after the Big Bang, showing us that the universe was already busy building structures remarkably early on. But here's the crucial point. The Big Bang theory explains the expansion and evolution of the universe from an initial hot, dense state. It doesn't explain where that state came from. It describes the how, not the why. And when physics reaches that absolute limit, that moment before the beginning, things get very, very weird. In the world of quantum physics, our classical intuition about nothing breaks down. True, absolute nothingness, no space, no time, no energy, no physical laws, may not even be a coherent concept. Even what we call a vacuum, or empty space, is a seething, boiling cauldron of activity. Thanks to the Heisenberg uncertainty principle, energy can fluctuate wildly over very short timescales. This allows for virtual particles to spontaneously appear from the void, exist for a fleeting moment, and then annihilate each other, all without violating the laws of physics. This isn't just theory. This vacuum energy has measurable effects, like the Casimir effect, where two uncharged plates in a vacuum are pushed together by these quantum fluctuations. This leads to a mind-bending hypothesis. Perhaps the universe itself is the ultimate free lunch. Some scientists, like Alan Guth and Lawrence Krauss, have proposed that the entire universe could have emerged from a quantum fluctuation in a pre-existing quantum vacuum, a spontaneous event where space, time, and energy appeared together from nothing. In this scenario, the universe may have cost zero total energy. The positive energy of all the matter and radiation we see could be perfectly balanced by the negative energy of gravity. Think of it like digging a hole. You create a pile of dirt, positive energy, but you also leave behind a hole, negative energy. The net change is zero. If the total energy of the universe is zero, then its creation from nothing doesn't violate the law of conservation of energy. But even if that explains the origin of energy and space, it leaves us with another, equally profound problem. According to our standard model of physics, the Big Bang should have created equal amounts of matter and its mirror image, antimatter, for every electron, a positron, for every quark, an antiquark. And whenever matter and antimatter meet, they annihilate each other in a burst of pure energy. If they were created in perfect balance, they should have destroyed each other completely, leaving behind a universe filled with nothing but light. Yet, we exist. You exist. The stars, the galaxies, everything we see is made of matter. For some reason, matter won. The current thinking is that for every billion pairs of matter and antimatter particles, there was just one extra particle of matter. A tiny, 1 in a billion asymmetry was enough to build the entire cosmos. This is called the problem of baryogenesis. Physicists have been hunting for the source of this imbalance for decades. Experiments at labs like CERN have found subtle asymmetries, a phenomenon known as CP violation, in the way certain exotic particles, like B mesons, decay. They don't always behave as perfect mirror images of their antiparticles, but the asymmetries we've measured so far are far too small to account for the vast amount of matter we see today. This mystery alone keeps physicists awake at night. When science reaches these hard limits, when the data runs out and the theories can only speculate, we find ourselves returning to the domain of philosophy, which has grappled with this question for centuries. In the 17th century, the German philosopher Gottfried Wilhelm Leibniz framed the ultimate question with perfect clarity. Why is there something rather than nothing? He wasn't satisfied with "it just is." He proposed what he called the principle of sufficient reason. This principle states that everything that exists must have a reason or an explanation for its existence. You exist because of your parents, who exist because of their parents, and so on. This chain of explanations can't go on forever. Leibniz argued it must terminate in an ultimate explanation, something that is its own reason for being, a necessary existence. This is often called a first cause, or unmoved mover, a concept that forms the bedrock of many theological and metaphysical arguments. For theists, this necessary being is God, a transcendent creator who exists outside of space and time and willed the universe into being. For pantheists, the universe itself might be that necessary being, existing eternally in some form, with no need for an external creator. But there's another, more unsettling possibility: absurdism. This view challenges Leibniz's core assumption. Maybe the universe doesn't owe us a reason. Maybe the principle of sufficient reason is a human rule, not a cosmic one. Perhaps the universe simply, without any deeper explanation. The question, why, might be a fundamentally human question, meaningless to a cosmos that just exists. Back in the world of physics, the quest for a deeper explanation continues. The biggest challenge in fundamental physics today is to unite our two best theories of the universe: general relativity, which describes gravity and the large-scale cosmos, and quantum mechanics, which describes the bizarre world of the very small. They are both incredibly successful, but they don't agree, especially at the extremes, like inside a black hole, or at the moment of the Big Bang. A theory of everything, could revolutionize our understanding of existence. For example, theories like loop quantum gravity suggest that space and time aren't smooth and continuous, but are made of tiny, indivisible, discrete units. In this view, you can't zoom in forever. There's a fundamental pixel size to reality. This could mean that the singularity of the Big Bang, a point of infinite density, never truly existed. Instead, the Big Bang might not have been a beginning, but a big bounce, a transition from a previous collapsing universe. And then, there's the multiverse. Some theories, like eternal inflation and string theory, predict that our universe isn't the only one. Instead, it might be just one bubble in a vast cosmic foam of countless other universes. Each of these universes could have different fundamental constants, different physical laws. In most, life would be impossible. Gravity might be too weak for stars to form, or the forces holding atoms together might be different. If that's true, it offers a radical answer to our question. It's not surprising that we find ourselves in a universe with laws perfectly tuned for our existence. We couldn't exist anywhere else to ask the question. This is the anthropic principle. It doesn't explain why the multiverse exists, but it reframes our own existence from a near-impossible miracle to a statistical inevitability. This idea is highly speculative and, for now, completely unproven and perhaps untestable. But it shows how the question can shift from why this universe to where are we in the grand scheme of all possible universes?
We asked the biggest question imaginable. Why does anything exist? We've journeyed through the science of our cosmic origins, the philosophical debates that have raged for centuries, and the speculative ideas at the very frontier of human knowledge. And after all of that, the honest scientific answer is, we don't know, and perhaps we never will. But maybe that's the most beautiful part of the answer. The universe exists, and against all odds within it, a tiny pocket of that universe became self-aware. It produced conscious beings capable of looking back out at the cosmos and asking questions about existence itself. The universe is not just the answer, it is also the question.
So what do you think? Is our existence a brute fact, a statistical accident in a multiverse, a logical necessity, or the act of a creator? Is the question itself the most important part? Share your thoughts in the comments. We'd love to hear your perspective. And if you want to keep exploring the hidden workings of the universe and the biggest questions we can ask, subscribe to this channel. Thanks for watching, and never stop asking questions.
The tech tower, that will